Hi everyone. So in this video, we're going to be talking about a new way to describe a graph using something called parametric equations. So we're not actually going to be doing any calculus in this video. We're first going to be kind of getting comfortable with how parametric equations work. And then in the next video, we'll see how we can do some calculus using these equations. So the idea behind parametric equations is that basically, like I said, it's a new way to describe a graph, and we'll see that there's some kind of new things that come along with this new description. So far, if you think back to, in this class and basically every math class you've taken in the past, most graphs, and I'm going to use the word curves here. Curve just is a kind of a generic term for a graph. That's, it could be a function, but maybe it's not a function. It's just kind of a general word to describe a graph. So most curves you have seen in math classes so far have been expressed in the form, so you either have y as a function of x, or sometimes you'll have x as a function of y. So for example, you might have a function like y is equal to 4x minus x squared, right? That's describing y as a function of x. And so when you have an equation like this that's describing one variable as a function of another variable, so in this case, y as a function of x, we're kind of thinking of x as being like our independent variable, right? So for example, maybe you could think of x as representing time. And then this relationship is telling us how is y changing as x changes, right? So this basically describes how y changes as x changes. Because, if you think, just picture making a table to graph this, right? You would first write down all your x values, right? And then you would see, oh, what happens to y when x is this? What happens to y when x is this? And so, for example, let's say that this function here was representing the height of a ball after x seconds. You're thinking about the time kind of changing, and how does the height of that ball change as time goes on? So the way that we're now going to be in this video describing curves is, instead of describing y as a function of x or x as a function of y, we're going to describe both x and y individually as a function of a third variable, which we'll call t. And so I'll kind of write more details about this in a second, but one way you can kind of think about it is, let's say you wanted to describe the motion of a particle. And let's say that particle is not moving in a straight line, it's kind of moving to the left, to the right, it's kind of going in some kind of a pattern. Well, then that means that you would have to describe the horizontal and the vertical position both as functions of time. And that's really what this is all about. It's about describing horizontal and vertical positions both as functions of a third variable, which you can think of as representing time. So, parametric equations, or I'll say it like this, with curves defined by parametric equations, we see both x and y not as functions of each other, not, x is a function of y or y is a function of x. We see both of them as functions of a third variable, t. And so we'll see an example in just a second, but we'll think of, for example, x is going to be a function of t, and then y is also going to be some other function of t. And by the way, so why are these called parametric equations? Well, this variable t is oftentimes referred to as the parameter. And parameter basically kind of implies the fact that this is the variable that's kind of changing. We're allowing t to vary, and we're seeing what happens to x and y. Okay, so let's do an example to start off with to see kind of how you can, when you're given some parametric equations, how you can kind of make sense of them and see what the graph actually looks like. And that's going to really be the main focus of this video, is going to be graphing different parametric equations, as well as we'll see that there's a way to take parametric equations and turn them back into something that more looks like this, right? So that's going to be something called eliminating the parameter. So we'll get to that in a little bit, but mostly we're going to be focusing on actually graphing these. So the first example we're going to look at is we're going to graph the curve defined by so these can be written in a variety of ways. Sometimes you'll just see a list of what x and y are. Sometimes they'll be like this in these kind of brackets. I think on your homework, they often put them in these brackets, so I'll write it like that. So x is a function of t, so we write x of t is equal to t squared minus 2t. And y of t, so y is also a function of t, is equal to t plus 1. Okay, so how do we make sense of this? Basically, we want to make a table, and we're going to look at different values of t and then see what comes out for x and what comes out for y for each of those different values of t. And once we have those different values, then we'll be able to plot some points for what we get for x and y. So one thing, and I think this will become clearer once we actually draw this picture, is that t is kind of like an invisible variable. So you're never like plotting t itself in this picture. This is still the x-axis. This is still the y-axis. So the t is kind of behind the scenes, and it's just helping us figure out what x and y actually are. So let's plug in a few points. We'll plug in -2, -1, 0, 1, and 2. Okay, so how do we find these points? Well, basically we just go to our two equations here and look at what they give us, right? So to find x, we're looking at this equation here. And so we just plug in t. So what do we get if we plug in -2 for t? Well, we get -2 squared is 4 minus -4. So altogether, that gives us a value of 8. And then how do we find y? Well, now we just look at the equation that has y in it. Actually, maybe I'll do this permanently. Let me do a quick little color change here. So that's your x equation, that's your y equation. Okay, so what would y be? Well, now we just plug in t equals -2 into this bottom equation, and we get -2 plus 1 is -1. So now when we go and actually graph this part here, this tells us our point. So we're not graphing t. T is just kind of, again, in the background. The only thing we're actually graphing here is the point that we got for x and y. So we have the point 8, -1, and that's the first point on our graph. Okay, so what's the next point? Well, now we're going to plug in -1 for t. And so if we plug in -1 to the first one, we get 1 plus 2, so we get 3. And then we plug in -1 to the second equation, and we get 0. And so that means that the second point on our graph is going to be 3, 0. So that's here. And then the next one, we plug in 0, so we get 0 for the first one. And for the second one, we get 1. And so that tells us that our third point on our graph is the point 0, 1. Then we plug in 1 for t. And for the first equation, we get -1. And for the y equation, we get 2. And so we have the point -1, 2. And then we plug in 2. And so for the first one, we get 4 minus 4, which is 0. So we have 0 as our x coordinate. And then for y, when we plug in 2, we get 3. And so we have the point 0, 3. So 0, 3. And so, this keeps going, and we'll see once I start to fill this in what shape it is. It's a sideways parabola. And so even though we didn't plot these points, I'm going to kind of keep sketching the graph because all it would take would be to plug in some more, t values, and we would continue to get these different points. And so one thing that's really important about parametric equations is that not only does it give you a picture, this picture kind of has a direction to it, right? Because we started at t equals -2, and then we kind of worked our way up. And so sometimes what people will add onto these drawings is these arrows. So these arrows are meant to denote the direction that this graph is going. Because what we'll see in actually just a couple of minutes is that you can have another set of parametric equations that gives you the same shape, but with a different direction to it. So when I say that t is invisible, it does influence your graph, right? What does it influence? It influences the direction that this graph is kind of traveling. But it doesn't show up explicitly as a coordinate. The x and the y coordinates are the things you're actually graphing, and t is kind of what's dictating the way that that graph gets written down. So, I know that it's kind of weird to think of there being some component of time or direction in a graph, but again, think about if you're graphing, for example, the trajectory of a particle, how is a particle moving as time goes on? This is a really good way to do it, right? Because you'll end up not only with a picture that shows the path that this object took, but it also shows the direction that it traveled. So there's another thing that we can do with parametric equations that also kind of makes them useful, which is we can kind of restrict the time period, restrict the t values that we're actually referring to. So I want to take this same example. I'm just going to kind of copy and paste this below, and we're going to just make a quick little change to it. So let's say that instead we add, or not instead, but in addition, we added in this statement where we said that we're only graphing this for t being between 0 and 2. So how would that change our graph? Well, now we would only be including the points that happened here, right? From t is equal to 0 to t is equal to 2. So this is the part of the graph that belongs with t being between 0 and 2. And so what would our graph look like? Well, it basically would not include the first 2 points. It would only be this portion of the graph. And actually, wait, we have to stop at 2. So what was 2 was 0, 3. So actually, my bad, let me go back because, so in this, basically, if there's no restriction given for t, you can assume that t goes from -infinity to +infinity. So that's why even though we stopped our table here, I kept going, right? I kind of kept graphing the graph, and that's because there was no restriction given on t. But if there is a restriction given on t, you don't want to keep going, right? So really the only part of this graph we want is the part that starts at 0, 1, so that's here, and goes till there. So this would actually be the only part of the graph that we would want if we had the restriction from t equals 0 to t equals 2. Okay, so I want to do another example that we'll see in some ways is really similar, but we'll see that it's also different. So in this case, what I want to do is graph the curve defined by, so this time we're going to have x of t is equal to t squared plus 2t. And we're going to have y of t is equal to 1 minus t. So you might notice if you kind of compare this with the example we just did, the equations look pretty similar, and we'll see that that's intentional. So let's see how this one pans out. So let's do the same values of t. So we'll do t is equal to, we'll start at -2, -1, 0, 1, and 2. And we'll see kind of how this graph differs. So again, we're always plugging t into the first equation to get our x coordinate and the second equation to get our y coordinate. So if we plug in -2 to the first equation, we get 4 plus 4, and so that is still equal to 8. Or sorry, no, my bad. We get 4 minus 4, right? If we plug in -2, we have positive 4 minus 4, and so we get 0. I knew the 8 was wrong, so I was like, something's wrong with that. And then if we plug in -2 into the second equation, we have 1 minus -2, and so that gives us 3. And so the first point that we're going to graph on our graph is the point 0, 3. And then the next point we would get is, so we plug in -1, and that would give us 1 minus 2, so that's -1. And then for y, we have -1, or we have 1 minus -1, so that's 2. So our next point is -1, 2. And if we plug in 0, we get 0 for the first one and 1 for the second one. So we have the point 0, 1. If we plug in 1, we get, for the first one, we get 1 plus 2 is 3. And for the second one, we get 1 minus 1 is 0. So we have the point 3, 0. And then for the last one, if we plug in 2, we get 4 plus 4, and that's 8. And then 1 minus 2 is -1. So we have the point 8, -1. So you might notice that these are actually the exact same points that we got on the previous graph. So what's the difference? Well, if we go back to our original example, so without the restriction, the first point that we got was 8, -1. Right? That was the first point we got. And so our arrows we started there and we went this way. Whereas in this example, we actually started with the point 0, 3 and we ended with the point 8, -1. So again, because there's no restriction on t here, we can actually continue the graph a little bit further just to kind of flesh it out here. But what's important is that in this case, the graph is going this way. Right? Because we started with points that were up here and we moved towards points that were going this way. So even though the parabola is itself the same, it would not be completely correct to say that this curve is the same as this curve. You know, if we imagine that there's some kind of an object that's taking this motion, it would be the same path, but it would be doing that path in a different direction. So I want to show you one thing that's kind of a good tool that you can use for graphing parametric equations. I think it is really important that you can do them by hand and kind of get a sense of how that works. But this tool, which I'll also link on Canvas, is kind of a nice way to practice with this stuff. So this first one, this is our first function that we did in this video. And so we'll see that you put in what your maximum and minimum values are for t, and then it allows you to drag this thing along so you can kind of see this as like a path. So we'll see eventually it will go onto the screen. And so notice that it's tracing out the parabola in the direction that we said for the first one. And so here again is now this is going to be the same, or this is going to be the second example that we did. So t squared plus 2t and 1 minus t. And so what you'll see is that this is going to give you the same parabola, but it's going to come from the other direction. Right? So this one goes like this, whereas the previous example came from the other direction. Okay, so this is one way to kind of get a handle on what the graph of a parametric, a set of parametric equations looks like. But sometimes you also will want to be able to rewrite it as either, y is a function of x or x is a function of y. And so the way that you can do that is something called eliminating the parameter. So, oops. Eliminating the parameter. So the idea behind eliminating the parameter is that some sets of parametric equations basically can be re-expressed a different way. And so for some of them, you can find a way to re-express them in the form y is equal to f of x, or x is equal to f of y. And so how are we going to do that? Well, we're going to start by solving one parametric equation for t. And then once you get that result, you can substitute that result into the other parametric equation. Okay, so for example, the first example we did, right, we had x of t is equal to t squared minus 2t. And then we had y of t is equal to t plus 1. So when I say solve for t, you're not going to get, oh, t is equal to 5 or something like that. You're not going to get a number for t. You're going to get an expression that's either in terms of x or y. So for the sake of this kind of process, let's actually get rid of this x of t and y of t. Let's just rewrite it as x is equal to t squared minus 2t, and y is equal to t plus 1, just to kind of make it easier to manipulate these. So looking at these, which of these seems like it would be easier to solve for t, to isolate t? Well, the second one, right? Because the first one, you would have to do some kind of funny business with square rooting, or, in this case, I think maybe like completing the square. It just wouldn't be so friendly. Whereas for the second one, we can just say, okay, well, if y is equal to t plus 1, then that means that t is equal to y minus 1. And so then what can we do? Well, we can take our second equation. So our second equation says x is equal to t squared minus 2 times t. And we can just take this value that we found for t and put it into these ones. So that will give us x is equal to y minus 1 squared minus 2 times y minus 1. So if we expand this all out, we get x is equal to y squared minus 2y plus 1 minus 2y plus 2. And so this would be x is equal to y squared minus 4y plus 3. So if you were to go and pull up Desmos and graph this, you would see the same parabola that we've seen in these two examples, right? Or well, I'll get to that. Well, but it would be the same parabola that we saw in this example, right? It would be a sideways parabola. However, there's a little bit of kind of information missing. So one thing I just want to point out is that, eliminating the parameter is nice because it kind of puts the equation into a more familiar format. However, you lose some information when you do it, right? We can no longer tell which direction this, path was traced. We don't know which one it is. So I want to kind of make a note of that, which is that when you eliminate the parameter, you basically lose information about the direction. And this is another thing that we'll get to in our next example. Also that there's kind of this component of speed, of like how quickly the path is traced out. And again, we'll see an example where that comes up in a little bit. But yeah, so you're basically sacrificing, you're making your equation easier to understand, but you're kind of losing that special information that's given by the parametric equations. So just to kind of drive that point home, well, let's actually do the exact same process with the other parametric equations that we had. So the other two were x is equal to t squared plus 2t, and y is equal to 1 minus t. So we saw that that gave us the same parabola, right? And so really we should get the same, if we eliminate the parameter, we should get the same thing. So we had y is equal to 1 minus t. And so that would tell us, if we solve this for t, that t is equal to, so if we add t and then subtract y from both sides, we'd get 1 minus y. And so then if we take that and put that into our x equation, we would have x is equal to 1 minus y squared plus 2 times 1 minus y. So what does this come out to be? Well, we have 1 minus 2y plus y squared plus 2 minus 2y. And so we get x is equal to y squared minus 4y plus 3. So it matches exactly with the one that we found above, right? It's the exact same equation. It's the same parabola. But that ignores the fact that the path was actually traced out in a different direction in these two examples. Okay, so I want to look at another example of, so we're going to be graphing, and then we'll also see how eliminating the parameter works, because it's going to be a little bit different in this case. So in this case, we want to graph the curve defined by x of t is equal to cosine of t, and y of t is equal to sine of t. So maybe pause for a second and think about, without actually plotting points, if you have any guesses to what this is going to look like, because this should maybe remind you of something from like pre-calculus 2, from trigonometry. So we'll see what the shape comes out to be and why that makes sense in a second, but let's start to make a table. And I'm not going to do, oh, I'm sorry, I wanted to add one more thing here. We're going to restrict t to being between 0 and 2 pi. But when I make this table, I'm actually not going to go all the way up to 2 pi just because it just will take a while to do that, and I don't really think it's worth our time. I think we'll get a vibe for how things are going if we just do pi over 4, pi over 2, 3 pi over 4, and pi. I think, we can just say dot, dot, dot. Like, I think we'll get a sense of how things are going just by doing that. Okay, so what do we get if we plug in t equals 0 into our first equation? So we have cosine of 0, which is 1. So we're going to get 1 here. And then what do we get when we plug in t is equal to 0 into our second equation? We get 0. And so this is the first point we're going to graph, right? So we have the point 1, 0. Okay, so what about for pi over 4? Well, cosine of pi over 4 is root 2 over 2. And sine of pi over 4 is also root 2 over 2. And I believe, and let me just double check this real quick. I forgot to do this ahead of time. I think it's about 0.7, but let me just get a good estimate so that we can graph it. Yeah, it's about 0.71. So when we're graphing this point, we want to go to about 0.71, 0.71. So I don't know, that's going to be somewhere around here, I think. Okay, so next point we have is pi over 2. So if we take cosine of pi over 2, that's 0. And sine of pi over 2 is 1. And so our next point is the point 0, 1. So 3 pi over 4, so cosine of 3 pi over 4 is going to be negative root 2 over 2. And sine of 3 pi over 4 is positive root 2 over 2. So again, we have this like approximately 0.71, so somewhere like here. And then finally, for this table, if we plug in pi, so cosine of pi is going to be negative 1, sine of pi is 0. And so we get this point here. So let's connect the dots for what we have so far, and then we'll talk about how this would continue So we have a semicircle so far, right? And so if we were to continue this process, we would just continue to get a circle. And if we went 0 to 2 pi, that would give us the full circle. So why does that make sense? Like, why could you maybe figure that out without actually plotting these? Well, think about how the unit circle works, right? When you learned about the unit circle in your pre-calculus class, you learned that the x-coordinate is sine of theta, and the y-coordinate is, or sorry, I said that backwards. The x-coordinate is cosine of theta, and the y-coordinate is sine of theta. And that's exactly what we said here, right? These parametric equations we came up with are basically just, or that we were given, are basically just like the definition of the unit circle, right? Like, so we're basically just kind of drawing the unit circle using the x-coordinate being cosine of an angle and the y-coordinate being sine of an angle as we go through different angles. So another way to see that this is a circle, and then specifically the unit circle, is by eliminating the parameter. And so this one, the process for eliminating the parameter is going to be a little bit different. We're not going to solve this we're not going to like solve one of the equations for t. We're going to do something a little bit kind of more clever. So how could we eliminate the parameter here? Well, we have, for our two equations, right, we have, I'll just write them in this form, x is equal to cosine of t, and y is equal to sine of t. So how can we maybe like put these pieces together without kind of solving either of them for t? Well, what if we put together x squared plus y squared? So if we take x squared plus y squared, that would be taking cosine squared of t plus sine squared of t, right? We're just taking, what we said, like this was x, so we did cosine squared. This was y, so we did sine squared. But what is cosine squared plus sine squared? That's equal to 1. And so the form that we have with the parameter eliminated is x squared plus y squared is equal to 1, right? There's no longer any t in our equation. And how do we get rid of the t? Well, we didn't like substitute it out the way we did on the other ones. We just kind of observed that, partially it helps if you know that already that this is the unit circle, but it's just sort of kind of seeing a way that you could combine the x and the y that you're given that would kind of simplify the t away. So I feel like there was something else I wanted to say, and now it's leaving my mind. Let me think for a second. I guess another thing to mention here is that part of the reason that we had to eliminate the parameter the way we did is because this is not a function of x or of y, right? A circle is not a function of x. It's also not a function of y. You need to do a semicircle in order to have something to be a function of x or y. And so that's why it wouldn't even work to eliminate the parameter the way that we did for the other example. We're kind of forced to be a little bit trickier, more clever about it. So I want to look at one more example. And so this is going to seem fairly similar to the last one. So for this one, I want to graph, sketch the curve defined by. And so this time what I want to do is the x part is going to be x of t is not equal to cosine of t, but cosine of 2t. And y of t is going to be equal to sine of 2 times t. And we're going to do the same t values we did on the last one. So we'll do 0, pi over 4. Sorry, let me write this the other way. Pi over 4. Pi over 2, 3 pi over 4, and pi. And then we can kind of think about ... where it would go afterwards. Okay, so for the first one, we plug in t equals 0 into our first equation, and we get cosine of still 0, so that's still equal to 1. And then we take sine of 2 times 0, so sine of 0, and that is equal to 0. So our first point that we're getting is going to be the same as the first point we got in the last one. Okay, so let's see what now happens when we plug in pi over 4. Oh, and sorry, I forgot to add in this. We're still doing t to be between 0 and 2 pi. Okay, so for pi over 4, what happens when we plug in cosine of 2 times pi over 4? Well, 2 times pi over 4 is actually pi over 2. So we're no longer calculating cosine of pi over 4, we're calculating cosine of pi over 2. And cosine of pi over 2 is 0. And then same for sine, so we plug in not pi over 4, but 2 times pi over 4. So 2 times pi over 4 is pi over 2. Sine of pi over 2 is actually equal to 1. So the next point on our graph is 0, 1. And then if we plug in pi over 2, so we have to do 2 times pi over 2, and that gives us pi. So cosine of pi is equal to -1, and sine of pi is equal to 0. And so that gives us a point here. And then 3 pi over 4, well, 2 times 3 pi over 4 is 3 pi over 2. So cosine of 3 pi over 2 is 0, and sine of 3 pi over 2 is -1. And so our next point is 0, -1. And then what about pi? Well, pi would be 2 pi once we plug it in. So cosine of 2 pi is again equal to 1. And sine of 2 pi is equal to 0. And so that actually puts us back at this point. So notice that in this case, we actually did the whole circle, but it only took us from 0 to pi to actually trace out that circle, right? And so what would happen if we went from 0 to 2 pi? We would actually kind of trace over this twice. So let me kind of write that down. Basically what I just said is that we traced the entire unit circle just by doing t being between 0 and pi. So basically what that means is that if you're taking t to be between 0 and 2 pi, we trace the circle not just once, but twice. And so that's what I meant when I said I brought up the idea of speed earlier. If you think of t as representing time, so from 0 to 2 pi would be from like 0 to a little over 6 seconds, right? And so if we're thinking of an object moving during that time, this object is moving faster, right? Because it goes around the circle twice in the same time period, where this one would go around the circle only once. You would have to go all the way from 0 to 2 pi. And I know we didn't fill out the whole table, but if you did, you would see that going from 0 to 2 pi would be just enough to go around the circle. But because for this one, our input wasn't just t, it was 2 times t, that caused us to kind of jump through the angles more quickly and cover more ground in the same time period. But another thing I just want to point out is that, again, if we wanted to eliminate the parameter, we could basically just do the exact same trick we did in the last example. Right, so we know that x is equal to cosine of 2t. We know that y is equal to sine of 2t. And so if you take these and both square them, x squared plus y squared, you would now get cosine squared of 2t plus sine squared of 2t. But it doesn't matter what what the input is, as long as the input is the same in the cosine and the sine, it's always going to be true that cosine squared plus sine squared of the same input, that they both have the same input, you'll always get 1. And so the form without the t in it would still be x squared plus y squared equals 1. And so that's why I said earlier that when you eliminate the parameter, you kind of lose some information. In this case, we lost the information of how quickly we moved around the circle. So this is something I'm going to ask you to kind of think about on today's worksheet, but there's also ways that you could change around these parametric equations a little bit, where you would still get the unit circle, but you would get it going in the backwards direction. Or you could figure out a way to write a unit circle where instead of starting at 0, 1, it actually starts at 1, 0. So there's lots of different ways to get the exact same shape, but some of the details will be different when you change the equation up. So I just want to show you one more thing on this kind of grapher, just to show you a couple of other just kind of cool examples. So this is the one that actually, if you go to this grapher, and like I said, I'll link it, this is the one that defaults to it. So it's x is equal to sine of 2t plus 3 times sine of t, and then y is equal to 2 times sine of 3t. So if we go and see what kind of trajectory this makes, it does this. And then notice it starts to repeat itself. So that's what I mean when I say that, like on our previous example, you know, it would continue to trace out the same graph. But yeah, so one thing that's just really cool about parametric equations is it is a good way to describe curves that look like this, curves that have kind of a lot of like different parts of them going on. And so I want to show you one more example that is especially kind of complicated. So I don't know if anyone else, maybe you all are too young for this, but when I was growing up, I had a toy that was called a spirograph. That was like, it's like this plastic wheel. I actually still have one now. It's like this plastic wheel where you put a pencil or pen in and you kind of go around. I'll write it down when I go back to the notepad in a second, so you can Google it if you're curious. But the patterns that you get from using that spirograph tool are very similar to the ones that you can get by using parametric equations. And so there are people who actually figure out, you know, what would be the parametric equations we need to, you know, create this spirograph pattern. So let me just show you this one, because this one is particularly intricate. So it goes through kind of a shape like that, and then notice it kind of repeats the same pattern but shifted, and it kind of keeps going around and around and fills itself in. And at some point, I think it starts kind of repeating itself. But you know, that's just one example of something you could get. And as soon as you kind of switch around, so this was sine of t plus 0.5, sine of 5t plus 0.25, cosine of 2.3t. As soon as you just nudge any of those numbers a little bit, it's going to change the shape. And so there's a lot of different interesting shapes that can emerge. You know, we don't unfortunately really have time to get into that, but I just wanted to kind of show you an example so you could see that, you know, there's a lot more possibilities out there with parametric equations, and you know, I'd encourage you to kind of look into those yourself. So let me just write down here in case you're interested. So the toy I was talking about is called the spirograph. So if you look that up on YouTube, I'm sure you'll find like videos of people doing it, and you can see how it looks a lot like what I just showed you on that grapher. All right, so that's it for today. Like I said, in the next video, we're going to be talking about how to actually use some calculus with these parametric equations. So I'll see you next time.